Okay, so this slide is introducing the concept of the head-related transfer function, or abbreviated HRTF.
Right. Basically, your notice it follows. So we have a microphone in free space, and we have this straight line at 0 dB. Notice that once we put the mannequin in there, we actually have amplification here at this frequency, and so this is occurring at like just a little over 2 kilohertz. So at that frequency, we have about 15, almost 20 dB of amplification occurring because of the resonance in our ear, okay? And that's because of the concha and the inner ear, the tube that's in there.
Because of genetics, that's about the frequency where a baby's cry will be.
So I'm going to see if I can demonstrate this. I got it to work in here the other day when nobody was in the room. So I'll push that out of the way. So the idea is, pretend this is an anechoic chamber with a free field. And we're going to see if we can output a signal from this speaker and EQ it till it's flat, and then measure the same response through Kimar's ear. Okay, so that's the response at this microphone position from that speaker. So what I'm going to do is I'm going to export this curve, the relative response curve, with all points to get the most accuracy, and just save it over top of that. And now I'm going to specify that I want to EQ out the speaker, so I'm going to choose a relative EQ and import the file that I just exported. And then tell the system that I want to invert it. So now, if I do an appended measurement, I get the same response. I think I see here. Let me try that again. Okay, so relative import. Invert. There, I think what I forgot to do is click OK. So now I have an EQ, and I'll append a measurement. So that's pretty good for flattening that little speaker. Okay, so we have our level graph. So now, at the position of the reference microphone, we're getting a purely flat response. So you can see, of course, it's different in level by quite a bit, but you can see that large increase around 2.5K, which is essentially a crude measurement of the head-related transfer function.
So the question is if you were doing something with, say, like mufflers, if you worked at Harley or something and you wanted to get that sweet sound, would you just put a microphone in free space and listen to the muffler, the sound that's coming from the muffler, or would you want to use Mr. Kimar?
So there you go. This is the relative response relative to 500 hertz in this case. So you can see that great big peak of about 12 to 15 dB centered around 2.5 kilohertz. So to do this measurement properly, this would be done in an anechoic chamber. And as Bob mentioned, you get a different head-related transfer function for each angle of incidence. So not only in a horizontal plane, but in three-dimensional space.
It fundamentally just shifts this just a little bit one way or the other, just depending on which angle we're at. But it's the same curve.
So you can actually translate a measurement from inside the ear simulator into the free field. And essentially you would take that inverted curve and subtract the levels in dB or divide them in linear units. I get asked the question sometimes, I've had customers say, well, I want a separate calibration for the left ear and the right ear. Well, when you're using headphones, quite often just the effect of positioning the headphone on the pinna has more effect than the calibration difference between the left ear and the right ear. So it doesn't really make sense. There is an IEEE standard, P1652, that covers this. And they use the concept of the orthotelephonic reference. So in a telephone conversation, the reference measurement is from a person talking to a person listening, facing each other 1 meter away. So that's the orthotelephonic reference. And you use the, it's called the DRP, or the drum reference point. So the measurement is taken at the microphone, which corresponds to where the eardrum is inside our ear canal. And the reference is from that DRP to 0 degrees on axis in the free field. So this reference to the free field is used for hearing damage studies, those types of applications. And the reason for that is there's a huge body of data for sound levels that occur in the environment, but they're measured with basically a sound level meter out in a free field. So if you want to correct the level measured inside the eardrum and compare it to sound levels measured in the environment, you have to correct it to the free field. This standard that we're going to talk about more later to do with headsets and the maximum allowable sound pressure level, that uses this technique where it corrects the measurement in the ear from the DRP to the free field. Now, as we mentioned, there's a different free field HRTF for each angle in 3 dimensions. This data is, the polar plot here is from the KEMAR manual that shows the different polar dispersion patterns for compared to angle of incidence. And the plot in the right is some data that Jacob from Gras gave me in Excel. And these are the free field drum reference point to free field HRTFs for 4 angles, 90 degrees apart in a horizontal plane. So you can see in the picture on the left, this is how it would be measured in an anechoic chamber. Now there's also a diffuse field head-related transfer function, and this relates the measurement from the diffuse field to the drum reference point. A diffuse field is a sound field where the sound is random incidence and the same almost everywhere in the field. In a laboratory situation, you can recreate this in a reverberant chamber. So you would create, you would have multiple speakers typically pointing into the corners that have uncorrelated noise sources, and you try to create a sound field that's uniform everywhere in the room. And then you can measure the transfer function into the drum reference point. Now, what the graph in the lower right shows is I took those 4 curves that we saw in the previous slide and averaged them together as a power average. And you can see as you sum the data for 360 degrees, you approach the diffuse field correction. So if you were to sum all of the HRTFs for an entire 3D space, you would arrive at the diffuse field correction, or diffuse field HRTF. So this, using this corrected frequency response is probably a better design target for designing the listening experience of headphones. If you want a desirable listening experience in loudspeakers, you try to design a curve that's flat to give a neutral frequency response. Well, if you design a curve that's flat inside a simulator, you're going to have a big dip that corresponds to this HRTF. So you might want to consider using either the corrected free field correction or the diffuse field correction as the design target for the frequency response of your headphones. But there's a note here. This IEC 60268-7, they allow frequency response measurements by 2 different means. An objective measurement with a head and torso simulator like KEMAR, or a subjective measurement where a person listens to headphones and then listens to a speaker and they try to estimate the frequency response manually. And the reason that they allow this, there's a quote in there, "No known objective method produces a flat frequency response characteristic from an earphone which is subjectively judged to produce wideband uncolored reproduction." So basically they're saying nobody can agree on what is good. When you look at the calibration sheet, you'll see a great big resonance that's up around 10 kilohertz. That's very got a high Q. And it's really this head-related transfer function that you should use to relate the measurement inside the ear to the free field.